Hi everyone, I am Xiang Gua. I am currently a PhD student at Northwest Polytechnical University in Xi'an, China. My supervisor is Professor Yuchao Dai. Today, I will introduce our work accepted by Asian Conference on Computer Vision 2022. The title is Neural Deformable Voxel Grid for Fast Optimization of Dynamic View Synthesis. First, let me introduce the background of our work, which is the dynamic neural radiance field. The dynamic neural radiance field is currently a very popular research topic. It aims to synthesize novel views images of dynamic scenes. It is one of the extensions of the original work of neural radiance field, which promotes the representation from static scenes to dynamic scenes. With the development of the NERF, papers on dynamic neural radiance field appears quickly in the past 2 years. These works achieve impressive results on various types of datasets. Here, I give 3 examples. The D-NERF uses a canonical-based representation and warp dynamic scenes to a single canonical static scene to render images. NSFF estimates scene flow to regularizes the dynamic radiance field optimization. The Hyper-NERF extend the canonical representation to a higher dimension space, producing more realistic renderings and more accurate geometric reconstructions. However, the existing dynamic NERF methods generally require a lengthy per-scene training procedure. All these methods use one or more big multilayer perceptron to model the dynamic field and the radiance field. For each pixel, the method requires hundreds of inferences of these perceptron. This will cause hours or even days of training. Based on this factor, we propose a dynamic radiance field method, which could finish training in minutes, rather than hours or days. I give a comparison of training process here. The left is the training process of previous method D-NERF, and the right one is ours. It is obvious that our method is training much faster. We summarize our contributions as follows. First, we propose a fast deformable radiance field method based on the voxel grid representation. Second, we design a deformation grid to store the 3D dynamic features and adopt a lightweight MLP to decode the feature to the deformation flow. The MLP is lightweight, which could reduce the inference time. Third, our method produces comparable results with D-NERF but only requires 20 minutes for training, which is at least 70 times faster. In this section, I will introduce our method in detail. This is the pipeline of our method. To render an image at any time step t, we march a ray from the camera center and get the points that this ray intersected with the voxel grid. To render the color of this ray, we need to get the density and color of each point. So, we first use deformation module to estimate the deformation flow, which is delta p. This flow could get the position of this point at the canonical time. In canonical space, we propose a canonical module to model the density and color of the whole 3D space. So, we could get the densities and colors of these 3D points by trilinear interpolation. Finally, the color of the ray can be rendered by standard volume rendering algorithm. Next, I will introduce these modules in the following slides. For deformation module, we propose a deform grid and lightweight MLP. The deform grid contains learnable deformation features. The lightweight MLP accepts the position p, time t, and the sample deformation feature, and then estimate the flow of this position. We could get p's position at canonical time by adding the flow to its current position. After we move all 3D points from time t back to the time canonical, we need to model the radiance of this static scene at canonical time. We propose 2 voxel grids and another lightweight MLP. The first grid is density grid, which contains the density of each voxel. So, we could get the density of 3D points by simple trilinear interpolation. The second grid contains color features. The lightweight MLP accepts sampled color features, the ray direction, and the position to estimate the color of these points. Once we get the density and color of the sampled points, we could render the color of the ray by standard volume rendering formulation. One should be noticed is that we estimate an occlusion mask by deformation module, and we mask out the points which are estimated to be occluded. From this design, you can find that we replace the big MLP with voxel grids combined with lightweight MLP. With this design, we could replace the inference operation of this big MLP with the interpolation operation and inferences of these lightweight perceptron. This would reduce the time consumption significantly. Moreover, there are more designs to save training time in our method. To further reduce training consumption, we propose to filter empty 3D points using a coarse-to-fine training strategy. First, in coarse training stage, without any knowledge of the scene, we can only set this loose yellow bounding box and train our model. After coarse stage finished, we could find all object points at each time step and combine them together to get a geometry prior. With this geometry prior, we could get a much smaller red bounding box for fine stage training. This helps to filter most empty space. Also, this prior could be used to filter sampled points. For example, without filtering, all these sampled points in dark gray need to be processed in coarse stage training. With the prior, we could filter most sampled points in fine stage training. Moreover, with this prior, we could know that these light gray points are not located in object area and have no effect on final colors. So, these points could be removed. With this coarse-to-fine training strategy, we can further reduce the training time of our model. This is the loss functions we used, which are pretty standard. The first three are photometric losses which are commonly used in this area. The next loss is the norm of the deformation, as we hope most of the points to be static. The final loss is the total variance of the deformation feature, which is used to ensure the spatial smoothness of the deformation. In the following section, I will present some of the results. This the quantitative comparison with DNERF on synthetic dataset. As shown in table, our method could achieve comparable image quality. For training speed, we could see that our method is at least 70 times faster than DNERF. Also, the render speed is 10 times faster. Here are some visual comparisons. Please refer to our paper for more details. Here are the results on real scene dataset. We can see that our method could achieve comparable results and finish training with around half an hour. We visualize the learned deformation features in Deform Grid of Deformation module. This row shows the balls are bouncing on the ground in this scene. We then slice the deform grid along this axis. Then we visualize the feature by separating them into three-dimensional images. The figure shows each slice in a row. The highlight images here showing that the features learned correct deformation patterns of the bouncing balls. That's all for our paper, and thank you for watching. Here is our lab page and project page for more information. Feel free to ask questions in the chat or visit our poster during poster session.